Hello everyone, we are from PES Modern College of Engineering, PUNE. Our project name is Design and Development of Lithium Pherophosphate Battery with Smart BMS. My name is Shivji Pramodit Pathak.
My name is Soham Marisha Shivdi.
My name is Siva Barasek Chavan.
My name is Shweta Arishante.
So let's see the demonstration of our project.
The objective of our project is to design and develop a smart, safer, efficient and environmental friendly battery. This is just a type of lithium ion battery, and we have just changed the chemistry, like we have used different cathode material for this battery. In lithium ion batteries we have used lithium cobalt oxide as a cathode material, and here what we have done, we have changed cathode material from lithium cobalt oxide to lithium ferrophosphate. So what it provides benefits, like if we consider the cost, it is little bit decreased due to the less use of lithium. Like we have just used 4% of lithium in this battery. It also provides various advantages over lithium ion batteries, like considering energy density, discharge rate, specific energy density. If we consider this point, the thermal runaway of lithium ion battery is near about 45% to 55%, but in this lithium ferrophosphate battery, thermal runaway is near about 105 to 135 degrees Celsius, and the energy density of this battery is decreased, and specific energy of this battery is 90 to 160 watt hour per kg. Energy density is 325 watt hour per liter, and of this battery which we have used is of 3.2 volt and 80 ampere hour. It also, there is improvement of cycle life of this battery. The normal lithium ion batteries having 2000 charging discharging cycles, but if we consider the lithium ferrophosphate battery, it has a 3000 cycle life. So we have manufactured a battery of 1 kilowatt hour, 12.8 volt and 78 ampere hour. So we have done a connection of 4S VP, means 4 cells are we have connected in series, and one that is in parallel. So we have used a smart BMS system for this, and we are using CCCV charging mode for this battery. So this battery manufacturing process includes various steps, and firstly we have manufactured the cells, and for that we have gone through the various stages. Like this manufacturing process is mainly divided into 3 stages, like electrode sheet manufacturing, cell integration and the formation. So these stages also includes number of stages, like slurry mixing, electrode sheet coating, calendering, slittering, electrode sheet creation, winding, stacking, liquid injection, capacity division and testing. And after the manufacturing of cell, we have just assembled the battery in 3 stages. These cells we have arranged in a 4 series configuration, and we have used a smart BMS system for this battery. And this smart BMS, what the working of this smart BMS, normally in the battery management system, what we can do is we can monitor and control the temperature, voltage and current of the battery, but by using this smart BMS system, we can monitor and control the temperature, voltage and current of each cell, including overall battery. So we can also provide a protection of over current, over voltage, under voltage and short circuit. So this battery is used for various purposes, like we can use for the various applications of electrical vehicles, UPS, energy storage, smart grids, and in utility scale stationary applications. And as the main motto of manufacturing this battery is to use in electrical vehicles, we have used a load of 60 kilowatt, and we have used 4 bulbs which we have connected in parallel with this switch with the use of the switches. And we are cross checking all the results with this ammeter, and we are getting these results in smart BMS app. So we are checking status of this battery with like state of charge, state of health, current, voltage.
Let's we check the characteristics of our LFP battery, that is SOC, charging and discharging of battery, then current, temperature of our battery. This is our resistive load. By using this load, we are checking the characteristics of our battery. This is a ammeter, DC ammeter, and this is a smart BMS app. By using this, this is a Bluetooth connection. So we are connected with mobile and checking the characteristics of our battery. So now we are switching on one by one this headlights bulb, and cross checking with this DC ammeter and checking in this smart BMS app. So by turning on this first lamp, we are checking the current flowing in this battery is near about 3.5, and we are cross check it with this DC ammeter, that it is also 3.5. It is minus because we discharge our battery. So by connecting second switch on, then it is near about 6.4, and it is, that is 6.8. So it is increasing by connecting our load. Then we are connecting our third lamp. It is near about 10.5, that is 10.2. So we are checking that our battery discharge by using this resistive load. By switching on our fourth LED lamp, the current is flowing in this battery is 13.4. So we are cross check with this app, that is, it is also 13.4 ampere. So
now let's see the working of our electrolyzer. Currently the battery is being connected. So the current through the electrolyzer here is 18 ampere, approximately 18 ampere, and the bubbles are already being generated. Bubbles generated on the positive side are of oxygen, while on the negative are of hydrogen. Those generated bubbles will get transferred to the tanks. Like for this is a hydrogen tank, so the gas generated here will be hydrogen. The bubbles generated here are of hydrogen. Those generated bubbles or hydrogen molecules gas will be then transferred to the buffering bag.